More than 100 million passengers boarded regional air carrier and corporate flights last year. There are more than 2,000 planes in the regional fleet and more than 12,000 jet and turboprop airplanes in the U.S. corporate fleet. Annual usage of these aircraft is climbing. All airlines are under pressure to fly rigorous schedules, often in challenging weather conditions. Regional airline and corporate pilots routinely encounter more atmospheric icing conditions than large transport because of the typical altitudes at which they fly. Moreover, a significant number of aircraft they fly rely on pneumatic boots for de-icing. Therefore, even pilots seasoned at slugging it out in icing conditions should find it helpful to examine the latest information about icing from NASA and the FAA. With new instrumentation and data gathering techniques, the body of icing knowledge is expanding every day. In addition, detailed reporting and careful investigation of icing-related events has produced new insights into icing encounters, crew, and airplane response. Pilots will be particularly interested in the latest research on the flight dynamics of iced aircraft and appropriate reactions to these conditions. The purpose of this video is to review the fundamentals of aircraft icing, enhance the pilot's ability to assess hazardous icing conditions and understand its effects on the stability and control characteristics of the aircraft, present strategies pilots can use to detect and safely exit a hazardous icing encounter, and finally, discuss briefly the phenomenon of supercooled large droplets, or SLD. Although icing is a routine operational factor, some accidents and significant incidents have occurred during flight in icing conditions. The risks associated with flight in icing, however, can be significantly reduced. To begin with, let's discuss some airframe ice protection basics. Now, ice protection systems are designed for either anti-icing or de-icing. Anti-icing equipment prevents the formation of ice. De-icing equipment removes ice after it is built up to an appreciable amount. Now, most anti-icing systems installed on aircraft today use heat to evaporate on contact the supercooled water when it strikes the protected surface. On turbine-powered aircraft, heat to the anti-icing system is usually supplied by bleed air. On aircraft with limited or no bleed air, electrical power is used to supply heat to the aircraft's protected surfaces. Some aircraft use a combination of both methods. When there is insufficient heat, droplets that strike the airfoil will not fully evaporate. It is possible that these droplets will run back until they reach the unheated portion of the airfoil and freeze. These might form rivulets and eventually a ridge of ice. Aircraft that use bleed air usually have warning systems to inform the pilot that power is too low to provide sufficient heat. Frequently, this occurs when engine power is reduced during descent or holding, when the volume or temperature of the bleed air is reduced. While some airfoils may tolerate runback ice better than others, this situation can become very serious. The ice protection system cannot remove this ice, and it may continue to build up and cause even greater aerodynamic problems. Unlike anti-icing systems, de-icing systems are used to remove ice after it has accreted on the protected surface. Although there are several methods available to remove ice from airfoils, the most common is the pneumatic leading edge boot. When activated, air pressure rapidly expands, then deflates the boot. These actions shatter the ice on the protected surface and break the adhesive bond with the boot, allowing the airflow to carry the ice particles away. Under some conditions with temperatures just below freezing, supercooled drops impacting the aircraft surface can remain liquid and run back for some distance before freezing. If this happens, ice can form aft of the boot and cause a situation similar to the runback conditions described before. Until recently, pilots had been instructed to wait for the ice to build up to a certain thickness before activating the boots. Pilots were taught that if the boots were activated too early, the ice might not crack off, but instead possibly expand to the shape of the inflated boot and remain in that position. And this would leave a gap between the boot and the ice so that subsequent boot cycles would not remove the ice. This phenomenon is referred to as ice bridging. A recent technical and operational information indicates that modern pneumatic boots characteristically do not have ice bridging problems. Current emphasis has been towards activating the de-icing system at the first sign of ice accretion. But for some aircraft, the manufacturer's AFM still recommends the traditional method of operation. Thus, be sure to consult and follow the manufacturer's AFM for your particular aircraft. Ice bridging had been a problem with some early boot technology that had very wide tubes and slow inflation and deflation rates. However, with today's modern technology, smaller inflation volumes and quicker inflation times do not support the ice bridging mechanism. No manufacturer of regional aircraft has reported bridging during flight tests in natural icing. No accidents or incidents have been attributed to ice bridging. And pilot surveys state that ice bridging is virtually non-existent with modern boots. What does exist is the ice that forms between boot cycles, known as intercycle ice, and the ice which remains immediately after a boot cycle, known as residual ice. It is true that a large ice buildup will be removed much more cleanly than a small ice buildup. And when clearing small amounts of ice, there may be considerable residual ice present after the initial boot cycles. However, the ice that can build during the traditional delay before boot activation can be very hazardous in some flight regimes and on some airfoils. Be aware that at low speeds and high angles of attack, even small amounts of ice can have adverse aerodynamic effects on some wings. When a boot is continuously cycled, that means using the automatic system if installed, the overall ice contamination levels are minimized. Now let's take a look at how ice accretes on aircraft surfaces. In-flight icing conditions exist when the static air temperature is below freezing, some water in the cloud is liquid, and the size of the droplet is large enough to strike an aircraft component. The most important feature of the cloud that affects ice buildup on an airfoil is the amount of liquid water in the cloud, or LWC. Also important is the size of the water droplets. In addition, air temperature, aircraft speed, shape and size of the airfoil also influence the amount and shape of ice that can build up. The type of ice that forms can be rime, glaze, or a mixture of rime and glaze. Rime ice forms when the droplet freezes on impact. This tends to occur when there are lower temperatures, less liquid water, and smaller droplets. These conditions produce an ice shape that has a milky, opaque appearance, the look of a freezer that needs to be defrosted. In many cases, rime ice appears as a sharp, pointed shape, although sometimes the ice shape conforms to the wing leading edge. On the other hand, glaze ice, known to most pilots as clear ice, tends to form at temperatures closer to freezing, with more liquid water and larger droplets. When the droplets impact the aircraft surface, the liquid water flows before freezing. This can lead to the formation of horns and ice shapes with rough surface features. These will significantly disrupt the airflow. This type of ice may be clear and almost invisible, particularly at night. However, it may also be very opaque and grainy. Each type of ice can be hazardous. But more important than identifying the type of ice is the effect it has on the aircraft. Each airplane is designed with specific airfoil and fuselage shapes to meet certain performance requirements. When ice accretes on these surfaces, the aerodynamic shapes are altered. This can cause significant performance degradation by decreasing maximum lift and stall angle of attack and increasing drag and stall speed. But most importantly, certain shapes, textures, locations, and thickness of ice can also disrupt the airflow over the wing or tail and create significant handling anomalies that may lead to roll or pitch upsets. Many pilots fly on a regular basis into areas of known icing. It is important to take full advantage of all cues that ice may be present, When moisture is present and temperatures are conducive to ice formation, pilots should be vigilant for early indications of ice accretion and should closely monitor the performance and handling of their aircraft. Many airplanes have some distinctive indicator to alert the pilot that ice is forming before a significant accretion is apparent on the airfoils. The aircraft might be equipped with an ice detector, or the pilot can look for ice on antennas, windshield wiper blades, prop spinners, or other sharp protrusions that would accrete ice earlier than an airfoil or engine component or propeller. Whether the best choice is to climb or descend to avoid ice depends on the location of the cloud top, cloud base, temperatures, the local terrain, and the power limitations of the aircraft. A higher altitude will allow more room for maneuvering, but typically there is more liquid water and cooler temperatures near the cloud top. On the other hand, descending can provide warmer air to shed the ice, but limits the altitude for recovery if a control anomaly occurs. Statistical analysis suggests that in 9 out of 10 cases, if the pilot varies altitude by 3,000 feet up or down, the aircraft will exit the icing environment, even if the aircraft remains in the cloud. Statistical analysis also suggests that in 9 out of 10 cases, if the aircraft travels 50 miles in a horizontal direction, the aircraft will exit the icing condition. Now let's look at the effects of this ice on aircraft performance. Performance problems, primarily due to drag increase, usually become apparent to the pilot gradually and may not be noticed until the aircraft is well into the icing event. Generally, the first symptoms of a performance problem are decreasing airspeed, decreasing climb rate, or a higher than normal power setting for a selected airspeed. Remember, even if the ice protection system is working, the increased drag from non-protected surfaces may still be significant. For example, a research aircraft experienced a 36% increase in drag with the glaze ice accretion on the unprotected surfaces with the ice protection system working. Ice accretions also reduce the maximum lift of the wing and cause the wing to stall at a lower angle of attack. This means an increase in stall speed. If you have a stall warning system, it may not adequately account for the ice contamination. Even if the warning system is adjusted for ice, stall warning may occur at or after wing stall. As always, the recovery procedure is to reduce the angle of attack. In summary, ice contamination will diminish the aircraft performance. Now, these changes will probably be subtle, but the increased drag will reduce the upper airspeed limit and climb rate for a given power setting, and the decreased maximum lift will increase the lower airspeed limit at which the wing stalls. Even though a small amount of ice may not cause a detectable performance problem, it may cause a controllability problem such as roll or pitch upset. In the 1990s, icing events involving turboprop aircraft have increasingly been attributed to handling events. This is where the pilot has difficulty controlling the aircraft roll or pitch or loses complete control of the aircraft. Why such an increase in handling events? The increase in handling events is a clear signal that there are aircraft configurations and icing condition combinations that are not fully understood by designers, authorities, and pilots. Uncleared ice on the wing can induce control loss in the lateral axis. Uncleared ice on the horizontal stabilizer can result in control loss in the longitudinal axis. Be advised, the following discussion of handling is targeted toward aircraft without hydraulically powered controls. Because they inhibit feedback from a control surface, hydraulically powered controls will not provide the pilot the tactile cues of an impending roll or pitch anomaly. When ice forms on the leading edge of an airfoil, it causes the flow to detach, creating a separation bubble. If the amount of ice on the leading edge is small and the angle of attack is low, the airflow will reattach. As either the amount of ice and/or the angle of attack increases, the separation bubble will move aft. Likewise, if the angle of attack decreases, the bubble moves forward. If the bubble bursts, That is, the wing is at a sufficiently high angle of attack, the flow does not reattach to the airfoil, and that section of the wing will provide less lift. If the separation bubble moves aft over a hinge point, the change in pressure may cause the control surface to move without pilot input.
Roll upset and pitch upset are manifestations of the same phenomena, separated flow. If you've got ice on any part of your wing or tail, you're going to get a separated region. The only question, how big is the bubble, how much of the core does it cover, and where does it occur in the span? A large enough bubble, due to ice or high angle of attack, will cause a handling anomaly.
Let's take a look at roll upset. A roll upset is most likely to occur when the aircraft is flying at slow speeds, that is, at a higher angle of attack, close to wing stall. If the aircraft enters into an uncommanded roll, whether the control wheel snatches violently or is simply ineffective in arresting a roll, you must lower the angle of attack. This is the only way to reattach the flow and recover from the roll anomaly. Even the most talented pilots may experience control anomalies or loss of control that sometimes characterize an icing encounter. In fact, data on incidents and accidents suggest that these types of events more often involve experienced flight crews. Some of the most treacherous conditions can appear with little warning. Remember that in cruise flight, the effects of icing may be very subtle and difficult to detect. However, icing, which seems to have little effect during cruise, can have significant effects when airspeed is reduced or the configuration is changed. If an aircraft is being hand-flown, the pilot has a better chance of detecting a roll anomaly before it becomes a problem. If the autopilot is engaged, there will be no tactile cues. However, one cue may be control wheel deflection without corresponding roll. If the situation continues to deteriorate, the autopilot may automatically disconnect due to high control force or angle of bank limits. Remember, if you experience a roll upset, the aircraft could be very close to a full wing stall because at least some, or possibly all, of the wing area is at or near stall. The procedure for recovering from a roll upset or wing stall is to immediately reduce the angle of attack. Even on a wing with large amounts of ice, lowering the angle of attack will provide for reattachment of airflow. As all pilots know, wing angle of attack can be reduced by lowering the nose, adding power to increase airspeed, and lowering flaps. Let's take a look at each. The quickest way to reattach the flow and regain control of the aircraft is to firmly lower the nose and add power as necessary. This will result in a loss of altitude, but this must be accepted in order to regain control. In fact, it is possible to lose significantly more altitude if the pilot does not initially lower the nose. Lowering the flaps when possible will lessen the severity of the roll event and aid the recovery. If used, the flaps should be deployed one notch beyond their present position. Full flaps should be deployed only with extreme caution. Of course, adding power is generally desirable. However, adding power by itself to increase airspeed while maintaining altitude is a slow process of reducing the angle of attack as the plane is accelerated. If a lot of ice has accumulated, available power may not be sufficient, depending on the aircraft.
The recovery procedure for an ice-contaminated wing will most likely differ from the procedure that you've been taught for recovery from a clean wing stall or approach to stall. That procedure emphasizes minimal altitude loss. The recovery is primarily accomplished through the addition of power. With an ice-contaminated wing, power alone may not be sufficient to recover the aircraft. The quickest way to recover an ice-contaminated wing is to firmly lower the nose while adding power. This will result in a loss of altitude, but the primary concern is regaining controllability of the aircraft.
In summary, lowering the nose and adding power is the safest initial response and offers the quickest recovery. If used, lower the flaps one notch. Lowering the nose will certainly result in an altitude loss, which could be significant. You may have to explain why you violated an altitude assignment, but a roll upset
or loss of control is an emergency situation that requires immediate action. Altitude loss must be considered secondary to regaining control. While wing stall with ice is more common, an ice-contaminated horizontal stabilizer can also lead to control anomalies or loss of pitch control. In most aircraft designs, the horizontal stabilizer has a sharper leading edge than the wing and is therefore a more efficient ice collector. If you notice ice on any part of the aircraft, chances are that it could have been accreting for some time on the tail.
As you can see here, the weight, which acts through the center of gravity, is forward of the wing center of lift. The combination of these two forces creates a nose-down pitching moment that the horizontal tail must overcome. This nose-down pitching moment increases as the trailing edge flaps are extended. Because the lift provided by the horizontal tail is in the downward direction, the flow over the lower surface is more critical. A small amount of ice on the leading edge of the tailplane can cause flow separation on the lower surface, just like it does on the upper surface of the wing. If the ice accretion is significant and/or the tailplane angle of attack becomes sufficiently negative, a separation bubble will be formed. The flow separation causes the stabilizer to become less effective.
Flap extension drives the tailplane angle of attack more negative, which causes the separation bubble to move aft. Secondarily, higher speeds also correlate to more negative angles of attack at the tailplane. Therefore, flap extension, especially at the high speed limit, forces the separation bubble toward the elevator, a movable surface. If the bubble moves past the elevator hinge point, the abnormal pressure distribution will try to drive the elevator down. Fortunately, in most cases, this does not occur without some significant, but sometimes subtle warning signs.
At first, the pilot may experience lightening of the controls in the forward direction. Other signs include the onset of pitch excursions similar to pilot-induced oscillations, and difficulty in trimming the pitch, or, if autopilot is in use, unexpected pitch trim motion. As the situation progresses, buffeting in the controls may be felt. In extreme cases, there may be a sudden forward stick movement. The nose may suddenly pitch down. If on final approach, it is possible that this may not be recoverable.
To recover from a tail stall, pull back on the yoke to resist the nose-down pitch and undo what you just did. Now, most likely, this will be to raise the flaps to their previous position. So, what are some safety techniques a pilot can use to avoid an upset event? The pilot must first correctly diagnose the problem. To do this, airspeed awareness, as it relates to airfoil angle of attack, is absolutely critical. Flow separation leading to wing stall typically occurs at a higher angle of attack, or at the lower end of the speed range for a given flap setting. Flow separation leading to tail stall typically occurs with full or partial flap extension and near the high speed limit for flap extension. Although the differences between tail stall and wing stall warning signs can be subtle, the recovery techniques are quite opposite. Recovery from a roll upset or wing stall requires flow reattachment on the upper surface, whereas recovery from a tail stall requires flow reattachment on the lower surface.
There are indications that, for aircraft whose thrust line is above the center of gravity, adding power might induce enough of a nose-down pitching moment to stall the horizontal tail. Also, for some aircraft, side slip may induce separation at the junction of the vertical and horizontal surfaces.
To summarize, remember that regions of separated flow called separation bubbles can form at various locations on the wing or tail airfoil. A separation bubble in the region of a control surface can cause serious handling problems, even though the airfoil is not yet stalled. Only when separation encompasses essentially the entire airfoil is the airfoil stalled. At this point, the effect of flow separation on the control wheel response is not well understood. However, with the aid of pilot reports, we surmise the following. A roll upset can occur when flow separates over the aileron. This might correspond to a reported auto-deflection or snatch of the ailerons. In this case, the aircraft might roll in response to the snatch. Asymmetric wing stall could also result in a roll upset. In this case, the roll control might feel sluggish or limp. A premature symmetric wing stall could result in a pitch upset. In all of these cases, the suggested recovery procedures are to immediately reduce the angle of attack by pushing forward on the yoke, adding power, and, if necessary, lowering flaps. Rudder control is also important. Flow separation at the horizontal tail can cause a pitch upset. A separation bubble ahead of the elevator hinge point could reduce elevator effectiveness. If the bubble extends aft of the hinge point, it could cause the control column to snatch forward. In the case of a tail stall situation, the suggested recovery procedure is to pull back on the yoke to resist the nose-down pitch, reduce flaps, and, on some aircraft, reduce power. In the intensity of a busy cockpit situation, the pilot must be able to correctly distinguish wing stall from tail stall to apply the correct recovery procedure. While operating in icing conditions, airspeed awareness is absolutely critical. A stick shaker may feel like elevator buffet. A stick pusher may be misinterpreted as elevator snatch. It is also possible on some aircraft for main wing flow separation to induce some elevator buffet. Proper awareness of airspeed will allow the pilot to correctly identify the event. Wing stall normally appears immediately after airspeed reduction or flap retraction. Tail stall normally manifests itself at higher airspeeds and shortly after flap extension. So, if the pilot determines that during or after flap extension or a nose-down input there is buffet or lightening of the controls, has difficulty trimming, or experiences pitch excursions, immediately retract flaps to the previous setting. Be prepared to pull back the yoke and be judicious with power. On the other hand, problems encountered after speed reduction or flap retraction, both of which raise the wing angle of attack, indicate a wing stall. Now that you have seen both the roll and pitch upset, you can see why it is critical that the roll recovery technique the pilot chooses, for example, lowering the flaps, does not place the tailplane at or near stall. A note about the use of autopilot. When flying in moderate or severe icing conditions, or even if ice is suspected after exiting the icing cloud, the pilot should hand fly the aircraft, or at least periodically disconnect the autopilot to get the feel of the controls and airplane response. Make sure your hands are firmly on the controls when you do this. The use of autopilot, particularly on aircraft that rely on aerodynamic balance for trim, may mask the control and handling anomalies that would normally be detected by the pilot at an earlier stage. Pilots flying aircraft without hydraulically powered flight controls may encounter extremely high control forces if the autopilot suddenly disconnects. Remember that in most icing encounters, the aircraft is flyable, but the operational speed or angle of attack margins have decreased.
Another area of concern for pilots flying in icing conditions is the phenomenon known as supercooled large droplets, or SLD. This phenomenon is currently under intense study by NASA, the FAA, and the National Center for Atmospheric Research, and others. SLD refers to droplet sizes that are larger than what is currently required for aircraft certification into known icing. Freezing rain and drizzle of any intensity are forms of SLD. The droplet sizes in freezing drizzle can be as large as 500 microns. Freezing rain droplets can reach 3,000 microns or 3 millimeters in diameter. Freezing rain and drizzle are dangerous because of their potential to accrete ice aft of protected surfaces. freezing rain and freezing drizzle are both observed and forecast as surface meteorological conditions. SLD, whether it is freezing rain or freezing drizzle, when observed on the surface, is typically found below 3,000 feet AGL. However, it has been observed to extend up to 9,000 feet AGL. It is also possible for SLD conditions to exist only at altitude and not survive to the surface. Again, the vertical extent is typically a 3,000-foot band, but can reach significantly wider. Ice pellets reported at the surface are a good indicator of SLD aloft. In recent years, encounters with SLD conditions up to 18,000 feet have been reported.
Be aware, no ice protection system is currently designed for flight in SLD conditions. There is no aircraft today that is protected for flight in freezing rain, freezing drizzle, or any SLD condition. Whether the aircraft is equipped with a de-icing or anti-icing system, encounters with SLD icing conditions are extremely dangerous because the ice accretion can extend well past the protected surface.
It is also possible to be in a condition where water can run back and freeze aft of the protected area. This might occur when turning on a thermal ice protection system after some ice has accreted or in certain meteorological conditions.
Ice forms after the protected area through two means. One is through direct impact, the second is through runback. In the case of direct impact, large droplets can strike not only the leading edge, but can cross streamlines and impact behind the leading edge, behind the protected area, and form ice. In the case of runback, there are various ways for this to happen, but essentially the end result is that water flows aft of the protected area and can form ice, again, in that unprotected area. This is an extremely hazardous situation because you now have ice where you cannot remove it, and you need to exit the condition, get to an area that's warm to melt the ice, or to an area that's dry to sublimate that ice.
If there is ice on the aft part of an unheated spinner, the aircraft is probably in an SLD icing encounter. On some aircraft, another visual cue of an SLD condition is ice accretion on the side windows.
If you confirm that you are in freezing drizzle, freezing rain, or any other severe icing conditions, it is important that you leave those icing conditions immediately. There is no one set recommendation for exiting icing conditions. Situation awareness is important. You need to know the surrounding weather, where the cloud tops are, the bottoms, the terrain beneath the clouds, before exiting. And then let the air traffic control people know what your intentions are, and let them know that it is a situation you must leave immediately.
The bottom line is that most ice protection systems do a pretty good job in what many people call normal icing conditions. But you have to use the system the way it was designed, know what's in the pilot's operating handbook. However, if you're in an unusual icing condition or a heavy icing condition, hand fly the aircraft. If you're slowing the aircraft or changing configurations, hand fly the aircraft. The airplane might be talking to you, and if you're on autopilot, you're not going to hear it. There is another situation, though, that you have to be aware of, and that's freezing rain, freezing drizzle, or SLD. If you find yourself in these conditions, treat it as an emergency. If you can't get out of it right away, declare an emergency.
If, however, you are in normal icing, review the icing information provided by the aircraft manufacturer in the Pilot Operating Handbook, and know the performance limits of the aircraft. Be especially vigilant for changes in control feel and maintain airspeed awareness. When operationally possible, it is always a good idea to change altitude or course to avoid any icing conditions. SLD encounters, however, are much more serious and may require a declaration of an emergency to escape.
We hope the information presented in this video provided a more thorough understanding of the symptoms of and recovery procedures for a roll or pitch upset. We also hope it helped in recognizing potentially hazardous icing conditions. If the aircraft enters an uncommanded roll, you must reduce the angle of attack. The best way to do this is through lowering the nose to recover the aircraft, adding power,
and if necessary, lowering the flaps 1 notch. If, on the other hand, after flap extension, the aircraft undergoes an uncommanded pitch, you must pull back on the yoke, retract flaps to the previous setting, and be judicious with power. Airspeed awareness will help you to correctly identify which event is occurring. Roll upsets and wing stalls occur at lower airspeeds. Tail stalls occur at higher speeds and typically during or after flap extension. If SLD conditions are suspected or confirmed, you must exit the condition immediately. With the wealth of experience pilots have in flying in icing conditions, combined with new insights on ice accretion being gathered every day, it is possible to significantly reduce icing-related accidents, making flying safer for pilots and the passengers they serve.